Okay. Once again, don't pay attention too much to the chapter. Just depends on what book we're looking at. This is going to be on current and resistance. So, there's a couple things that are probably very common to be heard. One is voltage, the other is current. Okay? So current is like the rate of flow. Voltage is like the push. So let's imagine we have like a highway, and on the highway you have a really large truck moving very, very slow. Okay, the size would be like the voltage, the current would be like how fast it's moving. So high voltage, big truck, low current, moving slow. Low voltage would be like a small car, high current would be like moving very fast. Okay, so anyway, here it's the rate at which electrical charge flows through an area. The three, like the equal sign with the extra one, just means it's defined as. So at some point, whenever we have an equation or whatever, somebody has to define something as something. So a force is defined as blah, blah, blah. Okay? So with that said, don't let this kind of bother you. You could just think of it as an equal sign. All right? And that's not an equation we're totally concerned about. Q would be the charge, and T is the time. So charge per time. So here we go. The units for current are coulombs per second. Okay? So coulomb is a measurement of charge. Okay? And obviously second is time. Now when we do current I, it's going to be in amperes. Okay? A coulomb per second is an ampere. All right? So this shows whatever going on here. We have like a cross-sectional area A. It's just some area, and charge is flowing through this wire. Okay? Normally wires are really, really small, right? This one is just blowing up kind of big. So conventionally, we know in real life that electrons are actually what's moving in a wire. So if we have the positive side of a battery and the negative side, electrons are going to be pushed from the negative to the positive. Negative, negative repel, pulled towards the positive. But you'll see that these arrows are the opposite way. So for whatever reason, and I probably read about it at some point, we always imagine the current being the flow of positive charge. We should also know that positive protons are not going to really flow, okay, at all through a wire, okay? But that's why it shows it going opposite of what we think. Current is going to be the opposite of what you would think, or the opposite of the movement of electrons, okay? Still, in my head, whenever I view and I think about current, I always think about what direction would the electron go. So it's kind of contradicting, sort of. Let's not worry about any kind of example problems for now. Okay? This one will be pretty straightforward, though. Current and drift speed. So drift speed is like the movement of electrons. Okay? So let's say we flip on a light switch. You instantly see the light turn on. Okay? So do the electrons just move so fast through that wire that they basically turn the light on? And the answer is no. Here's the deal. The electric field, okay, throughout that wire is going to be instantaneous. It's going to be the speed of light. But if we think about, again, a wire, and we have electrons in it, electrons are going to be really small compared to the wire. No matter how small the wire may be, the diameter. Think about how tiny electrons are. These electrons are going to start flying all over the place. Okay? Now, in the end, the net speed would be in one direction. Okay? But they're going to be colliding together. They're not going to all just in one direction. So that's why the drift speed is not going to be actually all that fast. It's actually relatively slow. Okay, so it definitely does not move at the speed of light. These are all colliding into each other. giving off their kinetic energies to other ones, and so forth and so forth. You might even have some end up bouncing backwards at times, which would actually cancel out some of the other ones. But the drift speed is relatively slow. I'm just going to put slow. I forget, we did this calculation in college, and without looking it up real quick, it's very, very slow. I forget how long it would take if you flipped on a switch, but it would take a long, long time. I think it'd take minutes for the electrons at the switch to actually get to the light bulb. I could look that up, and you could look that up. Right? Now, we're not going to worry about these calculations at this time, about the current and the drift speed. Okay? We have all these crazy things over here. Cross-sectional area, that's not a big deal. Number of mobile charge carriers per unit volume, let's not worry about that. Okay? Not worry about the example here. Down here, how do we measure these currents and voltages? This is called a multimeter right here. I think everybody's seen a multimeter. There's all these little click, 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 and you can switch to all sorts of things. You can use them to measure resistances. We'll get to that. Voltages, currents. You could also use a straight up amp meter, which this would be. It's measuring milliamps. So we don't a lot of times measure in amps. Okay, we measure milliamps. It's a much smaller unit. And down here would be a voltmeter, obviously to use to measure voltage. Okay, I don't know if you could see that. But a multimeter, you could kind of use it for everything. It's pretty handy. We have them in the classroom. All right, so what's this relationship between, we have current I, we have V for voltage, or it could be a potential difference too, okay? Potential difference, voltage, it's okay. We could kind of use them interchangeably at this time. And then R is the resistance. And just like it says, how much resistance is there, like in a wire? How much would it inhibit the flow, okay, of the electron? Okay? So if we want to look at, real quick, and it's probably going to come up here, the units. Okay, current is amps, voltage is, or potential difference, either is volts, and resistance is actually something called ohms. Okay, and we just label it as this. You'll see it down here. Okay, so current is directly proportional to the voltage. Okay, directly proportional. If this one goes up, that one goes up also. Okay, same amount. Double the current, double the voltage, all right, at least in this case. Now, here, resistance is defined as, once again, the defined, we have 3 lines, that's fine. V divided by I. So this change in V is not velocity. It is the change in the voltage, which we call potential difference. So let's say we have a wire, right, hanging between 2 telephone poles. And the voltage of that wire is, I don't even know what voltages are for that. Okay, we'll just make up stuff. 100 volts. And what's the ground going to be? 0 volts. What's the potential difference? 100 volts. Let's say for some reason something down here would be 10 volts. And we had a line going from one to the other. What would the difference be? 90 volts. Okay, so whenever you look at a battery and it says it's a 9-volt battery, that means the difference between the 2 poles is 9 volts. Okay, that's the potential difference. And we just call it the voltage. Okay, so this is turning into something called Ohm's law. Okay, there's Ohm. This is an omega. Sometimes you'll see I have a necklace on it. It's an alpha and an omega. That's the omega. Okay. We're going to come back to this. Let me look real quick ahead here. Yeah, we'll come back to this. All right, so here we go. This is called Ohm's law. Very important. V equals IR. Don't forget it. If you don't put the change in, that's fine. V equals IR. Voltage, current, resistance. Okay? Named after George Ohm. All right, we'll get to these all later. So what is this resistance thing? A lot of times, and I have a small one here, but I don't have it out. If you open up any kind of electronics, you're going to see something that looks like this. There's like this wire on each side, and then you'll see like this, it's probably like a brownish color, a brownish tannish color, and you're gonna see colors on them, okay? And you might see 4 different colors, okay? That is basically a color code system that is actually up here. If we were in class, we'd go through how to actually come up with those. I always look at the last color, and you can see down here the tolerance: brown, red, gold, silver, whatever. Most of the time you'll see gold and silver. So whatever you see gold and silver, I go to the other side and start there. Okay, so for example, if it was like brown, the next one was red, and then the other one was orange. Can't spell today for some reason. That's why I quit writing another word. You obviously saw that, hopefully. So, for example, first one, brown, it's a 1. Next one, red, is a 2. And then the third one tells you how many zeros, basically. It's a multiplier. Okay, so if it was orange, you would add 3 zeros. 1, 2, 3. And that'd be 12,000 ohm resistor. Okay, not something you need to do here, but just realize if you're ever playing around with electronics, you open them up and you see all these kind of resistors. All right. I don't know about current electronics. I know old ones, you definitely see a lot of it. Okay. So there's our Ohm's law. I could put like a million stars around this because we're going to be using this a lot. Okay. Don't worry about resistivity. We're not even going to get into electrical power. All right. So here's a little extra something. I think I kind of went back and forth with these notes a bit in the PowerPoint that I would do in class. So current, okay? It's measured in amps, A, coulombs per second. Already went over that. And there's 2 types of current. We have direct current, alternating current. If anybody's ever been to Niagara Falls, if you go on the Canadian side, you're going to see a statue of somebody I consider probably one of the greatest scientists, probably a bit nutty too, of all time, but Nikola Tesla. And there's a statue of him over there because of his idea for hydroelectric power and setting up the generators at the Niagara Falls. Okay, so what is direct current? So a battery is an example of direct current. We have a plus side, we have a negative side, and you have this push of electrons, right, from one side to the other. Right? Most common applications, battery. Very portable, okay, and fairly easy to use. A direct current person was Thomas Edison. Thomas Edison had a big feud with Nikola Tesla, and in class we would show videos or watch a video on this. It was interesting that they worked together for a period of time, or Tesla worked for Edison, and stuff happened. And at one point, Tesla, I believe, was actually digging like the ditches or whatever to actually lay the cables for Edison and Edison's direct current. So, and we'll get to something else that's kind of crazy if you want to look up a video on it. Alternating current is the movement back and forth of electrical charge. So, basically, let's just say when you flip a switch with alternating current, you're going to have this like push-pull, like of the electrons in a wire. Okay? Now, you think, wait a second, they're not actually flowing. All we need to do to get electricity is to get the electrons to move. Okay, so whether they're moving one way or moving the other way, it doesn't matter. Okay? That will still produce electricity. Now, why is alternating current better? Or what makes it better than direct current at times? Something in my throat. Well, one thing, a major thing about alternating current, allows you to transfer power efficiently electricity efficiently over long distances. Okay? And it deals with the use of transformers. Okay? If you look at motors too, you can have brushless motors with alternating current, less wear and tear, and that sort of thing. So this was Tesla. Oops. Tesla and Edison. 2 Ds? I'm not sure. And Edison. Okay? And So they kind of had a feud there, and Edison was pretty cutthroat to do whatever it took to let's say win, to make the most money, if you ask me. And so what he would do to try to prove that alternating current was bad, he would say, look how dangerous it is. And he actually used alternating current to electrocute like an elephant. And you could go on YouTube and see this. It's ridiculous. He would electrocute animals and say, see how dangerous it is? The fact is, you could have done the same thing with direct current. Okay? But it was like a grandiose kind of stage to show or to try to prove a point. And people would just look and say, oh yeah, it must be dangerous. But they wouldn't think like, how about direct current, right? So it's kind of crazy stories. Now here's my last thing on resistance. Okay. I already went over the units and all that. Don't worry about this, I didn't finish. Okay. And it deals directly with Ohm's law. Resistance remains constant over a wide range of voltages and currents. If wires and stuff heat up, like for example, why does the conventional light bulb light up, right? That has the little filament in it. It's because of resistance. When there's resistance, things heat up. Okay? You can even think about friction, right? There's resistance and your hands heat up. Electrons flowing cause resistance, and the bulbs would actually light up because of how hot they get. Okay? So once again, we're going to use that in Ohm's law. So why do we want resistance, right? Well, every component in an electrical device is not going to need the same voltage present. Okay, to produce the voltages needed at certain parts. Let's say of your calculator. Okay, you're going to have to create resistances there to limit the voltage to certain areas or certain components so they don't burn out. Okay, and we're going to get into that. Now, let's quickly talk about simple circuits. Okay, so we're going to focus on a couple things as far as a simple circuit goes. You see something like this? That is going to be the resistance. This is the switch. Okay? And our resistances can be, this is our source. It could be a battery, it could be some other kind of power supply. But our resistance could be anything from a light bulb to an actual resistor to anything. So you'll see a simple circuit look like this. You'll have a switch. It's open right now. It's not shut. Goes over to a resistor. Power supply. This. So this would be an open circuit right now, right? And then when we shut this, electricity would flow, okay, through our resistor. Okay? And in the next video, we're going to look at parallel and series resistors. Hopefully this wasn't too long. I think it was, though.